Let's look at infinite series, and this will be a mix of some intro ideas and context and theory and some examples. And the way I like to motivate this is actually to talk about power series first, informally, and then think about why you'd need to be really careful about series of numbers. So at this point, I'm hoping you've seen things like 1 plus x squared plus x cubed plus x fourth, that might be an expression that makes sense to define a function. And in fact, we have a hint that this actually defines a really nice simple function 1 over 1 minus x. And we'll come back to that exact example in another guise in a few minutes. There's another power series, famous power series, with coefficients 1 over n factorial. And in fact, it turns out that that's the power series for e to the x. There's a very big difference between these two, it turns out, as to what x's actually work. For which x's can you make sense of the limit here that's implicit in this infinite sum and say that it's really equal to x? And for which x's can you do that up here? Another one, very closely related to some of the stuff I've talked about already with Taylor polynomials and series, and this guy turns out at least sometimes, is minus log 1 minus x. So it's the log function with a little bit of shifting and modifying. We like to understand these things, and there's lots of other infinite series out there, but power series are our main concern. And the main thing we want to do right now is figure out questions like what I referred to a minute ago, which is when does this kind of thing make sense? For which x's does it make sense? So in particular, if I plug in a fixed x, we get a series of numbers, some sort of infinite sum. No variable anymore. That's not really how you write numbers. So for example, we could do x equals 1/2 in this first one. 1 plus 1/2 plus 1/4 plus 1/8. That's a really famous one. Does that have a sum? It sure does. We'll talk about that in a minute. We could also plug in, but we could also try to plug in, I'll put it up here, that same power series, we could try to plug in x equals 2 and get 1 plus 2 plus 4 plus 8 plus 16 plus... hopefully not much thought would convince you that that doesn't seem like it's even possibly going to add up to a finite number, and indeed, that's going to go off to infinity. And I'll talk about the explicit, precise definitions in a minute. But let's see, what if I plug 2 into this one? You might think, oh, plugging in a number bigger than 1 is just never a good idea. If I plug in 2 into this one, we're going to get 1 plus 2 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial plus 2 to the 4th over 4 factorial plus 2 to the 5th over 5 factorial. Eventually, these guys grow somewhat, but every time this is just multiplying by 2, this is multiplying by n. So it's going to multiply by 6, 7, 8. These actually are going to get small. They actually get small quite quickly. And so maybe this actually still works, even though I plugged in a moderately big number. This one is an interesting one. It's not too hard to see if you plug in x equals 2 or 3 or 4, it's probably pretty unlikely to converge. If you plug in x equals 1/2, probably pretty likely, and we'll talk about comparing it to like this example. But if you plug in x equals 1, you get this famous series. Does that converge? You're adding smaller and smaller amounts every time, but they're not getting small very fast. So, with that motivation, let's see what the task is. The task is just a little bit of notation, although I'll trust the book for that mainly. We've got a series, which is a formal infinite sum, and we want to know an infinite series. Does this converge? Does this define a number? And to make that more explicit, we say S sub n is the sum of those terms only up through n. It's called a partial sum. And so that defines a sequence of numbers. A sub 1 is the first S1. A1 plus A2 is S2. That's the second thing we'd write down. A1 plus A2 plus A3 is S3. That's the third thing. A1 plus A2 plus A3 plus A4 is S4, etc. And so we never actually, in this right now, we're not actually adding up an infinite number of things at all. And we never actually really do try to add an infinite number of things together. You just look at the pattern in adding more and more finite things together. And then if the limit of that sequence of partial sums exists, this is where you need to know about something about limits of sequences. If this exists, and let's say it's equal to S, then we're going to say that A1 plus A2 plus A3 ... and not stopping is equal to S. And we would use also the notation, let's say bring a dummy variable in, let's say k equals 0 to infinity of A sub k is equal to S. So there's a two-step process. One is to go from the terms to the sums, the partial sums, and then look at the limit of the sums. And one of the confusions is often at any point, are you looking at the terms or are you thinking about what happens when you add them together? So that's the sort of definition and nomenclature out of the way. And the truth is there's lots of methods, and we're going to learn some of them, sorry, bonk, to figure out exactly whether this converge or not. It's generally quite hard if you write down a random summation. It's rather hard to find an exact formula, but in fact, it turns out relating to power series gives us a hope of that in some cases. It's somewhat like integration, and it's really related to integration. It's a limit of a sum, somewhat like integrals are. Okay, and some of the intuition, you don't want to rely too much on intuition here because it can be slippery. But it's that A1 plus A2 plus A3 plus A4, an infinite series converges if the terms get small, in other words, go to 0 fast enough. And I'm going to put that in scare quotes because it's really quite slippery to be very precise about that. And that's why you have to have all these methods. Okay. The idea is like in our, let's go to this example. This is a great example to start with, and often people have seen this before this point. I claim these do go to 0 fast enough, and I'll give a little informal demonstration, then we'll be more formal in probably the next video, next part. Here's a nice informal demonstration of the fact that these do go to 0 fast enough and that we can actually figure out the sum. It's a little bit of a cheat because I happen to know the sum already, and I'm going to use that to interpret this in a nice way. I'm going to start at 0. I'm going to think of it as motion. I'm going to start at 0, and my job is to get to 2. And as I'm going, I just keep track of when I've got to certain very special points. I'm going, and I notice at some point I get to 1 unit. I've gone 1 unit. I tick that off and say, oh, okay, I've gone that much. And then I keep going, and I notice, oh, hey, I've gotten to 3 halves. That is halfway of the half the remaining distance to 2. Okay, and then as I keep going, at some point I will get half of the remaining distance. That's 7/4. That adds in this 1/4, which was half of the remaining distance. And then as I keep going, I notice at some point I've gotten to 15/8 because I've covered half of 1 more eighth, half of the remaining 1/4, etc., etc. And so the total turns out to be 2. Now, Zeno thought that you had to do, that proved you could never get to 2 because he imagined it would take a certain amount of time to get to here, and then a similar amount of time to get to here, and a similar amount of time to get to here, and a similar amount of time. But that's crazy. That's why I sort of try to say it as I'm going, and I just happen to notice these waypoints happening. Those waypoints are going to happen faster and faster and faster as I go. But each time I cover half the remaining distance, and so the limit of 1 and 1 plus 1 half and 1 plus 1 half plus 1/4, that's exactly the limit of where that endpoint is, and that's going to be 2. So we'll see a more careful proof in the next video. Okay, but so this is a good example, at least our first example, of a bunch of numbers that they go to 0 fast enough so that when you add them all up, it actually is finite. Now, you could ask, well, maybe as long as they're going to 0 at all, the sum is going to be finite, but that's not true. There's plenty of examples where the sum is not going to 0 fast enough. This is a great example. This is something that came up just a minute ago. That's called the harmonic series, because it has to do with like integer ratios with have to do with nice harmonic sounds of like frequencies and things like that. So they'll call the harmonic series. And in Stewart's book, they give the standard proof in just about any reference, Wikipedia, whatever. You can find a nice little proof that diverges. So these guys are going to 0, but not fast enough. So somehow we need to be a little bit more precise about, well, how do you know for a random, much more complicated bunch of terms, are they going to 0 fast enough or not? In particular, though, I want to end with one of our useful things, which is often called the divergence test. And that's simply if the terms that you're adding up don't even go to 0 at all, like if I'm adding up 1 plus 1 plus 1 plus 1, or 1 plus 2 plus 4 plus 8, or 1 plus like minus 2 plus minus 3 plus 4 plus 6 plus just some terms that don't go to 0 at all, then there's no way in heck that the sum can actually converge. Then the summation, the series, let's say, does not converge. This is a great example where you have to be really careful about the distinction between the terms and the series. The terms could converge to something. Like here, A1 is 1, A2 is 1, A3 is 1, A4 is 1. Here, the terms themselves converge trivially to 1. They're always 1. But when I try to add them up, or if I be more careful and I say the partial sums, those go to infinity, because that's 1, 1 plus 1, 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1. So for the series to converge to anything, the terms have to converge to 0. And this is what would be called the contrapositive of that statement. If the terms don't converge to 0, you're done. This is not going to define a number in any way, shape, or form. Okay, and so this is the extreme example of the motto, if it's when the terms go to 0 fast enough. And if they don't go to 0 at all, then it's easy. What's more subtle is, of course, when the terms do go to 0, we have examples like this where the sum still doesn't converge.